Hello students, you know who this is and you know what we're here for. Welcome to another exciting C++ lecture. At this point in the class I'm going to dispose of the begging and pleading for you to read the chapter before you review these slides. If you're here and it's this far into the class, hopefully you've gotten into a rhythm and you're going to move forward and stay with me. Okay, so let's get to it. Thanks. Chapter 3 continues where Chapter 2 left off with flow of control. Keeping with my strategy of moving slow during the foundational chapters, I will break Chapter 3 into 2 lectures. The first lecture will cover Boolean expressions and multi-way branches. Multi-way branches are a rather complex topic. And then in Part 2 of 2, we will cover more about C++ loop statements, and last but not least, Section 3.4, designing loops. As mentioned in the previous slide, Chapter 3 continues the discussion of flow of control. As we learned in Chapter 2, flow of control refers to the sequence in which lines of programming code are executed. So far, at the end of Chapter 2, we saw 3 ways to specify the flow of control. Actually, 2 ways and 3 techniques within those 2 ways. The first was a branch, an if-else statement that used a condition evaluated to true or false to determine which of the 2 branches, which of the 2 ways control would flow. And the last 2, while and do while statements, are loops that will loop over and over and over again. The primary difference being the minimum number of times a loop body is executed. In a while statement, the condition that determines whether or not the body of the loop is executed is before the body of the loop. So a while statement could evaluate, the condition could evaluate to false and skip the body of the loop, thus looping 0 times. That will never happen in a do-while loop because the do-while loop contains the condition to be evaluated as true or false, which determines whether or not we will loop, is at the end of the body of the loop. So the block of code within the loop is executed a minimum of 1 time before an evaluation is made, which determines whether or not we will continue, move back up to the do, and execute the loop statements. New methods described in this chapter are switch statements and for statements. We will get to those momentarily. A Boolean expression is an expression that is evaluated to either true or false. And they're evaluated using relational operators such as equivalency, less than, greater than or equal to, which produces a Boolean value. And Boolean values can be combined using and, or, and not, which also produce a Boolean value. A type bool, which is a data type, allows declarations of variables that carry the value true or false. Boolean expressions are evaluated using values from the truth table, which we'll show you in a minute in display 3.1. So here's an example. If going into this Boolean expression, y holds a value of 8, the expression, I'm not going to read it to you, is evaluated in the following sequence. False or true. Okay, if it's false or true, that's true. And then the not, which is in the outermost order of precedence, flips that value to the alternate, which is false. As promised, here's the truth tables, display 3.1. So when you string 2 Boolean expressions together with an and, Let's follow the truth table. If the first expression is true and the second expression is true, expression 1 and expression 2 evaluate out to true. Using and, that's the only combination that will evaluate expression 1 and expression 2 to true, because expression 1 and expression 2 have to be true. If either one is false in any order, or both are false, the entire expression is false, or is somewhat of the opposite. 3 out of 4 or evaluations are true, because expression 1 or expression 2 in any order just need to be true. The only way expression 1 or expression 2 returns a false is if expression 1 and expression 2 are both false. And not obviously turns a true to false and a false to true. When building Boolean expressions as conditions for branching or looping, try your best to not use the not operator. The not operator can be very confusing. And a word of advice from someone who's evaluated and written a lot of Boolean expressions: use parentheses. Even if you don't think you need them, parentheses are the safety net. They allow you total control over the order of precedence. If parentheses are omitted from Boolean expressions, the default precedence of operations is the not operations first, then relational operators such as less than or greater than next, then the and or operators. The and operators are next, and or operators are last. Items and expressions are grouped by precedence rules for arithmetic and Boolean operators. Operators with higher precedence are obviously performed first. Binary operators with equal precedence are performed left to right, and unary operators of equal precedence are performed right to left. Hold on for display 3.2 for more explanation on this. Here in display 3.2, we further review the precedence rules. The unary operators, which are plus, minus, plus, plus, minus, minus, and not, have the highest order of precedence, all the way down to the Boolean operation or. I'm not going to read them in order, but this is a really good slide for you to save or bookmark, however you do it in this electronic world. But this is very valuable. As for me, I don't like to have to remember all of these tedious rules, so I use parentheses to better control the order of precedence. It puts me in control of the expressions I'm building. This slide presents an excellent example of the precedence rules. The expression listed first, x plus 1 in parens, greater than 2, or x plus 1 paren, less than minus 3, is equivalent to the whole thing on the left side of the or being wrapped in parentheses, or the whole thing on the right side being wrapped in parentheses. It's greater than and less than have higher precedence than or. And it's also equivalent to what's listed below without the parentheses. As you can see, it gets very confusing, which is why I just use parentheses. I would have written this as the second statement, the middle statement, if I were coding this. So once again, evaluating x plus 1 greater than 2 or x plus 1 less than minus 3, use the precedence rules in display 3.2. First you apply the unary minus, and next apply the pluses. Now apply the greater than and less than, and finally do the or. I still find this, after years and years and years of looking at these types of expressions, I still find this a little bit confusing, which, not to sound like a broken record, Now I'm aging myself. Not selling a broken record, but I still like to use parentheses to control the order of precedence. It's just, I think it's easier to understand, easier to debug, and less confusing. C++ uses short-circuit analysis. Some Boolean expressions are not totally resolved in order to be completely evaluated. In this example, if x is negative, the value of the expression x greater than or equal to 0 and y greater than 1 can be determined. Remember, with and, both of them need to be true or the whole thing is false. So that can be determined by evaluating only x greater than or equal to 1. C++ uses short-circuit evaluation. If the value of the leftmost sub-expression determines the final value, or can determine the final value of the expression, as is the case when you have and, the rest of the expression is not even evaluated. Because we know if you have 57 ands strung together, if you evaluate the first 3 and they're all true, but you get to the 4th and that's false, the entire 57 are false. So why continue? Short-circuit evaluation is useful in preventing runtime errors. On this slide, there's a good example of a short-circuit evaluation that avoids a divide by 0 runtime error. So if, in this example, if the value of kids is 0, look at the second condition in the if statement. Pieces divided by kids. During runtime, that would get through the compiler, but during runtime, that would cause a divide by 0 error, which is bad. But by putting it in an and second to if kids not equal to 0, creates a short-circuit evaluation. So if that is false, if kids does equal 0, it never evaluates pieces divided by kids greater than or equal to 2, which is a divide by 0 condition. C++ can also use integers as if they were bools or Boolean values. If the integer equals 0, that equates to false. Any other number or any non-zero number is true. Now in a bool it's 0 and 1, but in int, if you have a 2 or a 3 or a 4, it's still true. Once again, here's another problem with the not operator. You want to avoid using the not operator whenever possible because it is confusing and it can cause problems. So here's an example where someone is obviously trying to say not time greater than limit. In other words, if time is less than limit. But that's not how this evaluates out. The not time is evaluated first, and what is that value if time is 36 minutes or 36? False or 0, since it will be compared to an integer. So the expression is further evaluated as 0 greater than limit, which is always false. This is very problematic and should be you should be very careful in using the not operator. I just don't like it. I find that almost always there's a better way of defining an expression without the not. Here is the example on the previous slide, restructured so, and using my friend's parentheses, time greater than limited is evaluated first because the parentheses trump the order of precedence, and if that evaluates as false, then the not flips it to true. Still not it's still not the clearest way to do this, in my opinion. I think I've been making this point all along. I like how the author states, just as not in English can make things not difficult to read. Yeah, the not operator obviously makes C++ expressions difficult to understand. It's not intuitive. So before using the not operator, try to express the same idea more clearly without it. And in most cases, you'll find that you can, just by rephrasing the expression. This slide presents a new data type, the enum or enumeration type. It's a type with values defined by a list of constants which are all integers. So an example of a declaration of an enum called month length, and this is how you declare it. You need the brackets, January length, and then equals 31, February length equals 28, comma in between each one, and you would go through all of the 12 months designating the length of the month. If when you first declare enums, numeric values are not specified or initialized, the variables are not initialized, identifiers are assigned consecutive values starting with 0. So here's an example. Enum direction, north equals 0, south equals 1, east equals 2, west equals 3. That is equivalent to that same declaration without the initialization, because by default the first numeric value is 0, 1, 2, 3, etc., etc. Another twist to the value assigned an enumeration constant is +1 more than the previous constant. So here's an example of an enum with an identifier name of my enum. 1 equals 17, comma, then 2 and 3 are not initialized. But because the one prior to 2 was 17, 2 will take 17 plus 1. It will equal 18. 3 will equal 19. And then we can go right back to initializing 4 as a different number. So 4 will be initialized to -3. And 5 will be, this is tricky, -3 plus 1, -2. Here's an enum example I pulled off the internet just to show you. We declare an enum days, and it holds numeric constants that coincide with the days of the week. Sunday being 0, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday being 6. So 0 through 6, 7 values. And then using days, we declare an enum variable called the day. We declare an integer j. We ask the user to enter the day of the week 0 through 6. I would have put 0 equals Sunday, 6 equals Saturday in that cout statement to make it clear. And then we use the day equals days j. J being 0 would mean Sunday, j being 1, Monday, 2, Tuesday, etc., etc., etc. And then there's a quick if statement evaluating the day if it's Sunday, and you can use the actual names in the enum declaration. If the day equivalent to Sunday or the day equivalent to Saturday, do the following. Feel free to cut and paste this and compile it if you'd like. Play around with it. We're not going to use enums too often in this class, but they are a unique variable type that was worth mentioning. That concludes section 3.1. Here is an exercise I usually do in the class. I provided the solution for the first part on the next slide. Write an enum definition for an enum named in order that takes 3 arguments of type int. The function or enum returns true if the arguments are in ascending order, otherwise it returns false. We'll look at that in a second. Actually, you'll look at that in a second. Determine the value of these Boolean expressions. You should be able to determine this. Assume count equals 0 and limit equals 10. Count equivalent to 0. If count is 0, it comes out true. It's a compound expression. And limit less than 0. Limit is less than 0. True and true returns true. Not parentheses count equivalent to 12. Well, count equivalent to 12 returns false, but the not flips it to the alternate, so that's true. Limit less than 0, that's false. So short circuit evaluation never gets, because it's in an AND, never gets to the second part. So limit less than false, or less than true is false. Because it's in an AND, it never evaluates the second condition. Here is the solution to the enum example given on the previous slide. I strongly suggest, I'm not going to read it to you. This is an exercise we usually do in class. We compile it and let students play around with the coding. I strongly suggest you do that also. Take a look, and let's move on to the next section. Okay, students, this is the beginning of section 3.2, a very fun section. I guess you can tell that I'm a nerd if I think multi-way branches are fun, but I do, and I openly admit it in public. So let's get going. This slide begins our discussion of multi-way branches. So far, the branching mechanism that we've covered is the if-else statement. It's a two-way branch, and a branch selects one of a number of alternative actions. In the case of the if-else, it's one way or another. Branching mechanisms can be a subpart of another branching mechanism. So in an if-else statement, if the condition is true, you can drop down to another if-else statement which would provide a multi-way branch. We'll look at that in a second. Here's an example, our first example of a nested if statement or a multi-way branch. A statement that is a subpart of another statement is called a nested statement. When you write nested statements, it's common practice to indent each new level of nesting. So in this example, if count less than true, if that is count less than 10, if that is true, it jumps down to another if statement. That is the nested if statement. We'll take a look at this in a little bit more detail. So here we have display 3.3, which is an if-else statement nested within an if statement. Now if count is not greater than 0, in other words, if that expression is evaluated as false, it skips over the nested if-else statement. However, if it's true, it drops down to another condition evaluated if score greater than 0. See out that statement. If score greater than 0 is false, it goes to the else of the nested if. That else is paired with a nested if, not the original if. On the next few slides, we'll review a nested if application and show how important it is to use care in nesting if-else statements. So the example is, we want to design an if-else statement to warn a driver when fuel is low, but tells the driver to bypass pit stops if fuel is close to full. Otherwise, there should be no output. So the pseudocode is listed here. If fuel gauge is below 3/4, then if fuel gauge is below 1/4, then issue a warning. Otherwise, gauge is greater than 3/4, then output a statement saying don't stop. Sounds reasonable. In following slides, we'll go into this deeper. Here is the first attempt at translating the pseudocode to C++, and a potential error that it could yield if not careful. If fuel gauge reading less than 0.75, it jumps down to the second if, the nested if. If fuel gauge reading less than 0.25, see out, fuel very low, caution. Else, see out, fuel over 3/4, don't stop now. Now this code compiles and runs successfully, but it has a logic error in it because the compiler pairs the else with the nearest previous if. To safeguard against this happening, we're going to block the code using brackets. So stay tuned. Braces in nested statements function like parentheses in arithmetic expressions. They trump the order of precedence. They control or tell the compiler how to group things. So I always use braces around substatements. Next we'll look at display 3.4, which uses braces in the previous nested if-else statement to better control the flow of execution. Here we see the actual C++ implementation of the program we've been discussing over the past few slides. And the nested if statements are now enclosed in braces, and that code is highlighted in, I guess you would call that light blue. And notice how the braces control the nested if statement, and no longer is the else statement paired with the first nested if statement, because the braces clearly identify that as what's done if the condition is true. If the condition is false, it's going to drop down to the else statement. So this is a great example of how braces help the programmer to control the flow of execution. I strongly suggest you download code 3.4. I put it in the timeline, compile it, and play around with this, maybe move the braces. I could sit here and lecture all day long about this, but unless you're coding this and making slight changes to see what the braces actually do, it will be difficult for this concept to sink in. Thanks. As mentioned previously, an if-else statement is a two-way branch. 3, 4, or more way branches can be designed using nested if-else statements. An example that we'll cover now is a number guessing game with a number stored in a variable called number, named number, and the guess in variable guess. How do we give hints? Stay tuned and you'll find out. Here we have excuse me, a series of nested statements used to implement the hints for our number guessing game. First, if ascertains whether or not the guess is greater than the number. If it is true, see out too high. Else, we go into another. So if the guess is less than the number is false, if guess greater than number returns false, it drops down to the else, which has a nested if else. If guess less than the number, see out too low, else, which is paired with the nested if. The only option left is that the guess would be equivalent to the number and you see out correct. Here is an alternative that prevents the code from creeping across the page, leaving less and less space. This alternative for indenting several nested if-else statements: if guess greater than number, see out too high, else if, you put the else and the if on the same line, and then another else if. Here is one more alternative to the solution we've been discussing. When the conditions tested in an if-else statement are mutually exclusive, the final if-else can sometimes be omitted. So here is an example where if the guess is not greater than the number and the guess is not less than the number, the only option, especially when we're dealing with ints, is that the guess is equivalent to the number. This slide shows the formal syntax for nested if-else statements, and in the next slide we'll look at a fully implemented example of a nested if-else statement. The next few slides take us through an excellent program example which calculates state income tax based upon varying requirements. The requirements are no tax on the first $15,000 of income, 5% tax on each dollar from $15,001 to $25,000, and then 10% tax on everything over $25,000. I typically do this in class with students. I strongly suggest, if this is an online or a hybrid class and you're working through this at home, that you download the code for 3.5 from the web study timeline and you take a close look at this. Put it in your compiler, run the program, maybe modify the criteria a little bit. Strongly urge you to do this. This is an excerpt from program 3.5. The code is available in web study, and you also have it with the textbook if you bother to register at that website that comes with the textbook. I'm not including the entire program because it wouldn't fit on this slide. And this is an example of a nested if statement, a multi-way branch that calculates a tax bill if one of three conditions exist. The net income is less than or equal to $15,000. Else if the net income is greater than $15,000 and net income is less than or equal to $25,000. Or the final condition is net income is greater than $25,000. Notice you don't need an if statement for that because they are mutually exclusive. It's not the first and it's not the second, it has to be the third. I strongly urge you to pull this down, put it in the compiler, run it, run a few examples of boundary condition net incomes, rate at $15,000, $25,000, etc., and see how it handles those different values. This is an integral part of the learning experience. And if you're in a hybrid or online class, we may not be doing this in the classroom. Thanks. Here we do some refining of the if-else statements. Notice the line if-else net income greater than $15,000 and net income less than or equal to $25,000 can be replaced with simply else if net income less than or equal to 25, because the computer will not get to this line unless it is already determined that net income is greater than 15,000. So restating that condition, net income greater than 15,000, is redundant and not necessary. Now we're going to take a look at another multi-way branch tool, which is the switch statement. It's an alternative that creates what I would call a menu system. Let's take a look at display 3.6. You have this code in the web study timeline, and I strongly suggest that you download it and put it into the compiler as we go over it on the next few slides. The switch uses a variable to select specific cases. Those cases represent the multi-way branches. In this example, which is highlighted in blue, light blue, we're asking the user to enter the value for grade. Grade is a variable that will be used to determine which branch of the switch is executed. And the different values for grade are obviously A, B, C, D, F, and there will be a default that is executed if one of those values is not entered. So if a user enters a value of Z, as in zebra, for grade, well, obviously that's not one of the options A, B, C, D, F in a typical academic setting. So we must have the default at the very end. Each case is selected based upon the value of grade. Then there's some output, and then there is a break statement, which causes the switch to end after it executes a specific case. This slide shows 4 sample dialogues from the previous program with the switch, and in each one a different case is selected. The first one, the user types in A, which becomes the value of grade and takes us to case A. Second is B, third is D, and then the fourth uses the default because it doesn't find a matching case, A, B, C, D, F. And the default has a cout that says this is not a possible grade, end of program. This slide shows the formal syntax for a switch statement. You must have a controlling expression, and then your cases have constants, and you must have a default statement to handle cases that are not listed with constants above. The controlling statement in a switch has to return a bool, an enum constant, an integer type, or a character. And then the value returned is compared to the constant values after each case. When a match is found, the code for that case is used. If no match is found, it will execute the default. A break statement ends the switch statement. If you omit the break statement, the code for the next case will be executed. And you might be thinking, oh, that's a problem. Not always is it a problem, and in many cases it's planned. Here's an example. You're asking the user in the previous example where they're entering a grade to enter a grade A, B, C, D, F. Well, what if you wanted to don't want to limit them to having to type in a capital letter? In other words, you would accept a capital or a lowercase a or b or c or d, f. Well, then simply list case. Here's an example for an A. List case A, uppercase, and then immediately following, no break, no statements, case lowercase a. So If the user enters a capital A or a lowercase a, the same code will be executed. Now, you do need a break after both of these cases. It's a really good idea to have a default statement to handle cases not clearly delineated within the switch. If no case label has a constant matches the controlling expression, the statements following the default label are executed. It's not mandatory that you have a default label, and nothing happens when the switch statement is executed if it doesn't find a matching case and there is no default. But it is good practice to include a default section. It might be obvious that nested if-else statements provide more versatility than a switch statement. But switch statements have certain applications, such as a menu is the perfect application for a switch statement. And we'll take a look at a menu in the code for 3.7 next. This slide and the next show the code for 3.7 from your textbook, and it's an excellent example of using a switch statement for a menu application. Unfortunately, this code doesn't fit on one slide, so you'll have to go back and forth between the two slides to see the entire switch statement and the entire program. But the user is prompted to choose 1, 2, 3, or 4 as options on a menu. 1 to see the next homework assignment, 2 for your grade, 3 for assignment hints, 4 to exit this program. And each one of those is used to load an initial value into the variable choice, which is an int. And then you see the switch, and in this particular example, each option, each case, is calling a function. Now, we haven't gotten into functions yet, but just look at that from the mile-high view. Each one of those functions, show assignment, show grade, give hints, is code that's coded in a function that's called, it executes, and then returns a value. We'll get to that later in this class. And that's not the part of this we're really being concerned about. It's the menu application of the switch. So let's take a look at the next slide, and you'll see a sample dialog. So here we have the remainder of the code in the switch and in the program, and a sample dialog. Now, the exact output will depend on the definition of the function give hints in this particular dialog. And that's kind of abstracted in this example. We're not really worried about the function or defining that function or what's in it, just that it is called when case 3 is executed by the switch. As we noted in the previous example, it's useful to have function calls in branches, but the problem here, and this is the author's deck of slides, we haven't yet lectured or studied function calls. So a function is simply code that exists, that's written outside of the main program, that's called, processing takes place, and then it returns a value to the main program. So we'll just gloss over that at this point in time. Each branch of a switch or case or if-else statement is what's called a subtask. And if the action of a branch is too simple to warrant a function call, which we're not going to study until later, use multiple statements within braces. In other words, block the code within braces. A block is a section of code enclosed by braces. Now, here's another concept we're going to introduce. Variables declared within a block are local to the block or have what's called the block as their scope. And they can't be reused outside of the block. And I'll show you that next in the code from 3.8. Here is an example of the concept of scope, which was introduced in the previous slide. Note the code in light blue, which is in a block. It's encapsulated within braces. A variable is declared within the block, double subtotal. Subtotal, because it's declared within a block of code, is only usable or is only accessible within that block. So later in the program, after that else if block is executed and we're back in the main, you can't use subtotal. It is a local variable local to that block. And we're going to talk about this at great length later in this course. And here's the remainder of the code and a sample dialog. Once again, I strongly suggest that you download 3.8, the code for 3.8, from the Web Study Timeline or whatever website you're using to download code from, and compile it and run it. More on statement blocks. A statement block is a block. It's not a function. It's not a function body or the body of the main part of the program. Statement blocks can be nested in other statement blocks, but this is not advisable. Nesting statement blocks makes the code very, very difficult to read, and it's generally better to create function calls than to nest statement blocks. And we will drill down on these concepts ad nauseum when we get into defining functions. Here's a concept that's confusing the first time you encounter it. If an identifier is declared as a variable, the same name identifier is declared as a variable in each of two different blocks, one within the other, then these are two different variables with the same name. I know that sounds bizarre, but their scope is limited to the block. One of the variables exists only within the inner block and cannot be accessed outside the inner block. The other variable exists only in the outer block and cannot be accessed in the inner block. This is called scope, and it is often a concept that confuses students. It's difficult to get your arms around this, so we'll take our time, and each time we encounter a scope issue, we will spend a lot of time describing the scope of variable. That's the end of section 3.2, and I'm leaving you with a little brain teaser. Take a look at this code. You may even want to put it in the compiler and run it. It is a brain teaser that helps students understand scope within block. And you have the same variable, x, declared and initialized outside and inside a block and its output. And I often find that the output generated by this code is sometimes confusing for students. So I strongly suggest you take this, put it in the compiler, and run it and experiment. Thanks. Although I record these lectures for various types of courses, I typically do put the solution to 3.2 in the timeline. So check to see if it is there. You have to understand that I record these lectures and then sometimes use them for a year or two, and things change. So, but at the point in which I'm recording these lectures, I did put the conclusion to 3.2 in the timeline. So take a look. Thanks again.